Hi, thanks for coming. This is Hayoung from Handong University. In this work, we investigated the best practice for applying continuous unilevel fuzzing with LibFuzzer to SAP HANA database. We found that the fuzzing is a promising way for discovering software faults in SAP HANA. At the same time, we found new challenges to resolve. We addressed these problems with change-aware selection and mutation scheduling. Continuous fuzzing is becoming a new way for guarding against software faults by running fuzzing for every release of the product along with its project lifecycle. This is a typical use case of fuzzing with system-level test. A developer writes code and makes a commit to a repository. Then the code is integrated automatically. And then the fuzzing is conducted, and if it finds failure, report back to the developer. System-level fuzzing is conducted for 24 hours or longer and uses a handful of test cases to test the entire system. Recently, fuzzing is applied for unit-level testing as well. The purpose of unit-level fuzzing is different from system-level fuzzing. Unit-level fuzzing runs for a short period, like a few minutes or few hours, and aims to test a large number of modules independently. So new challenges arose for fuzzing framework. First, it needs to quickly investigate changed code only. If a developer wants to do pre-commit check with the fuzzing tool, in such a cases, the fuzzing tool should not waste time to explore irrelevant code. Second, the optimal fuzzing setting will be different for each module. If developer cannot make fuzzing engine tightly fit to each module, it will make fuzzing ineffective. To find out if a large program such as SAP HANA DBMS can effectively use continuous unilevel fuzzing and address new challenges of the fuzzing, SAP HANA team and our team in Handong conducted an industrial project. SAP HANA is a full-fledged database system with a large number of modules. Developers constructed a large scale of regression unit test suites and run them continuously on test infrastructure. Our team investigated the best practices for writing unit-level fuzzing to supplement the unit test. As a first part of our project, we've systematically established test drivers for each module in this way. We grouped existing unit test cases by target function and analyzed all inputs to identify unique behaviors. Based on that, we constructed parameterized unit tests, and the inputs are collected as initial seed corpus. We constructed grammar-aware mutators so to specifically target each module. With provided test driver, test infra periodically conducts fuzzing and report new failures. For an effective issue report, we made a new module for deduplicating failures and utilizing the result of fuzzing inputs as unit test. As a result of it, we found 9 unknown bugs and achieved 4 times higher coverage for 2 HANA components. Despite these positive results with the LibFuzzer, we also found limitations for continuous unilevel fuzzing. As a second part of project, we created new techniques to alleviate the limitations. First limitation is that it is inefficient to conduct fuzzing from scratch whenever small code change is made. To resolve this inefficiency, we propose change-aware seed selection that reuse test inputs from earlier fuzzing run for conducting fuzzing with the following version. Second, grammar-aware mutators are not effective when it is not properly used together with random mutators. To resolve this, we created mutation scheduling strategies to effectively accompany grammar-aware mutators and random mutators. So far is an overview of our work. And in remaining time of this talk, I will elaborate on change-aware seed selection parts and how we improved rate of failure detection. Developer run a unit-level test even when the size of code change is small and the change happens only locally. In this case, general purpose seed corpus is ineffective for unit-level fuzzing because it is designed to cover a wide range of code regions. In conventional fuzzing practice, each fuzzing run uses the same general purpose seed corpus repeatedly. The seed corpus initially covers this range of functions. After 6 hours, cover this area, and it consumes a lot of time to explore entire functions. For the next version with local code change, fuzzing run tries to cover previously explored passes like the same manner as before. After a long time of redundant exploration, finally starts to investigate the changed code. Even though results of earlier version fuzzing exist, the conventional fuzzing throw them away and conduct fuzzing with same initial seed corpus. With this approach, time is wasted to test unchanged code. To resolve this inefficiency, we propose change-aware seed selection technique. So we are proposing new way for regression fuzzing testing by utilizing the test inputs from earlier version fuzzing with changed functions. The technique proceeds with the following steps. First, we conduct fuzzing with the general purpose seed corpus. With the generated test inputs, we do not throw this away and keep it with per function corpuses, which is the set of test inputs that cover each function. When the code change occurs, we find all functions where at least one of the code lines was modified, added, or deleted. Regarding the functions, we select the inputs from corresponding per function corpus. Finally, we conduct fuzzing for changed function. We used change relevant seeds instead of general purpose seed corpus. Sometimes the number of selected seeds can be too large. So we propose 3 seed selection strategies to control the size of the seed corpus. The details of strategies can be found in our paper. With this approach, the time to detect failure is reduced because inputs in per function corpuses position a fuzzer to quickly reach the changed code region. Here's the result. To evaluate the rate of failure detection, we designed case studies with 4 real-world faults that actually found in HANA repository. For each case, code change has 1 or 2 changed functions and 9 to 36 lines of code change. The table shows that the technique reduces failure detection time from 5 hours to 20 minutes, which is 15 times of improvement for C1. For the other cases, all seed selection technique reliably reduces failure detection time, and the average failure detection ratio is improved 4 times. It indicates that if a code change is not significant, the selected test inputs guide fuzzing to effectively explore changed code regions. Another observation is that best performing techniques were different for each fault case, which means developers have to make fuzzing setting tightly fit to each target. So far, I explained what our team has done and change-aware seed selection part. We did not cover mutation scheduling part, which is important as well. It can be found in our paper. This is the end of talk. Thank you for your attention.